Hello and welcome back to Dr. Logic Awkwardly Does Logic. We're currently in a series of proofs where I take the canonical model for a particular modal system and I demonstrate that the frame that underlies that model is actually a frame for that logic. So we saw this in the previous video with systems K, which was trivial, and T, by showing that because the T axiom is in every single maximal T consistent set, this forces the frame of the canonical model to also be reflexive. In this video, I'm going to do the same thing, but for system S4. So we take the canonical model for S4 and show that the frame that underlies this model is a frame for the logic. That means that we need to show that the frame is reflexive and transitive. Now, because axioms and their frame conditions, at least the ones that we've talked about so far, work in this sort of modular way, I already know that since S4 contains T, and we showed that the canonical model for T is reflexive, the canonical model for S4 is also going to be reflexive. It's exactly the same argument. So all I need to do is show that the frame underlying the canonical model for S4 is also transitive. And we will do this because of the fact that the 4 axiom, i.e. the one that corresponds to transitivity, is a member of every S4 consistent set. So let me bring up the whiteboard. Cross my fingers this time that I will be able to draw on it. Come on, come on. You can do it. Yay! I can draw on it. So what we're trying to prove is this. We've got our canonical model for S4, and we know that this consists of a frame and then a valuation. So what we need to show is that this is reflexive and transitive. And since we've already shown reflexivity in the previous video, it's just transitivity that I need to worry about here. That is, what we need to show is that for all maximal S4 consistent sets, gamma, delta, and lambda, the following holds. That if gamma sees delta and delta sees lambda, it follows that gamma also sees lambda. So this is what we need to show. What we will do is we'll start off by assuming the antecedent and trying to derive the consequent from this. So we will assume that for arbitrary gamma, delta, and lambda, we have that gamma sees delta and delta sees lambda. So that's fact 1, fact 2. This just means, by the definition of the R relation, so this is the same thing as saying that the box minus of gamma is a subset of the box minus of delta, and then this fact corresponds to the box minus of delta being a subset of the box minus of lambda. That just is the definition of our accessibility relation. So what this means, so what 3 means is that if box phi is in gamma, then phi is in delta, and also that if, this should be that the box minus of gamma is a subset of delta, and the box minus of delta is a subset of lambda. Forget those extra box minuses that I put in there. So what we get from 4 is that if necessary phi is in delta, then phi is in lambda. So that is just, again, writing out the definition of what the box minus notation means. So what we want to get is that what we need to show is that the box minus of gamma is a subset of lambda. In order to show this, we need to show that if necessary phi is in gamma, then phi is in lambda. So these are all the facts that we have from our assumptions. This is what we need to show. I will try to fit the rest of the proof onto this so that we've got all of the information on one page, but I will just have to write a little bit smaller. But what we need to show is a hypothetical. So we start off by assuming the antecedent and showing that we can get the consequent. So we assume that box phi is in gamma. Now, remember that the 4 axiom is a member of all of the maximal S4 consistent sets. So that means that box phi implies box phi is also going to be a member of gamma, since it's an axiom. And we also proved a lemma some videos back that says if you have a conditional in your maximal consistent set and you have the antecedent, you also have the consequent. So this means that also we have that box phi is a member of gamma. And now we can go back and use these other facts that we have. So I'm going to label this one as 5 and this one as 6. So by 5, we have that if box sum formula is in gamma, then take a box off and that result is in delta. Well, box phi is in gamma, so this means box phi is in delta. But 6 says if you've got a box formula in delta, then take off a box. The remaining thing is in lambda. We have that since box phi is in delta, we have that phi is in lambda. And if you go back up to what we needed to show, that's what we wanted. On the assumption that necessary phi was in gamma, we can show that phi is also in lambda, which is equivalent to saying that the box minus of gamma is a subset of lambda, and hence that gamma sees lambda, which is what we wanted to show. So, slightly messy, apologies for that, but a good exercise for you is to maybe sit down with your own piece of paper, write through the proof, a little bit less messy, a little bit more aligned, without some of the typos, and with everything nicely annotated so that you've got good cross-references and proper references back to your definitions. This is a really useful exercise to do, to take these sort of sometimes slightly messy verbal proofs that I'm doing and turn them into something written, and then go back to the textbook and see how does this compare with the written version that is there. Where there's deviations, are they just cosmetic? Or is this actually, have you missed a part? Have I missed a part? Do I have a typo? Who knows? It is impossible to write a logic textbook that has 0 typos, so could very well be. Not in this proof, I don't think. This is a pretty easy proof. Some of the proofs that we will see next are going to be more complicated because there are some frame conditions that don't just use universal quantifiers. Sometimes there's existentials. How do you demonstrate the existence of the relevant kind of world? That's actually super fun. So I'm probably going to jump past the results for B and S5 because they're a little bit boring and go straight ahead to the system or any logic that contains the axiom of convergence because that's a lot of fun. And it also illustrates something that the proofs that we've just seen doesn't. So join me again and we'll take a look at that. And soon we will have a big enough body of examples that hopefully you'll have a sense of how this whole process works before we go and do an example where it doesn't. Because that's the fun of logic. Until then, take care. Cheers.